Hello and welcome back. Today we'll be talking about binary numbers and round-off errors, which is one of the main sources of error when we do computing on your computer. So this is the first section of the next component of the class on error, and it's really important to understand where errors may arise when you do numerical computing. So the learning goals for this section are to understand some of the basic vocabulary about error, accuracy, and precision, to understand differences between the types of errors that we'll encounter, such as true error and approximate error, and to understand how computers store numbers. And that has a very significant reasoning for how errors occur when we do computations. And so we need to understand when we need to worry about the errors that might arise when we do computations. So you may have heard these terms before, accuracy and precision. So accuracy refers to how closely a computed or measured value agrees with the true value. And so, for example, in this example right here, they're all fairly close to the bullseye, but they're not precise. They're kind of individually far apart from one another. In another case, a precise archer might be doing it very close to one another, but it's far from the desired answer. So we'll be using these terms accuracy and precision when referring to the computing that we do. Ideally, though, our answers would be both precise and accurate. And so we're going to be talking about what is it that makes computing precise and what makes computing accurate. But first, just want to remind you that computational analysis gets used very widely within biomedical engineering. And every day, biomedical engineers use numerical methods using computers to find accurate and fast approximations to complex problems. And so this is an example where there's a 3D heart being simulated, and there's a heart attack that occurred right within this zone. And so there are waves of electrical activity that produce arrhythmias that can lead to sudden cardiac death. And so what they're trying to simulate here is test out different therapeutic strategies. And of course, they need those predictions to be both accurate, that will correctly tell you what may be happening in a real heart, and also fast so that they can get information back to the patient quickly. So there are really two types of error that we'll be discussing. One is called round-off error. Another is called truncation error. So round-off error comes from rounding of numbers due to the computational way in which numbers are stored within the computer. And so that's why today we'll be talking in more detail about binary numbers and the limitations of these binary numbers and being stored on the computer. And the other type of error we'll talk about is truncation error. So that's different. That's the errors that are made due to simplifying some of the mathematical approximations that we'll make. Such as if you do the series analysis, remember that from calculus, if you're cutting off higher order terms, that's an intentional error in order to simplify the problem. And so we'll be talking about that in a later lecture. But today we're going to be focusing on binary numbers. So first, get an idea of why we would care about binary numbers and the way that the numbers are stored in the computer. Let's think about a few different sort of simple games that we might play, kind of guessing what would happen in a given computation. Excuse me. So, for example, if we have 1 minus 3 times 4/3 minus 1, you'd typically think that would be 0, right? Let's go back to Python and check. So we said, so let's call this variable a, and we've got 1 minus 3 times 4/3 minus 1. And we see the value of a right here is not 0, it's 2 times 10 to the minus 16. Or let's look at, that's a little bit just disturbing, isn't it? Let's look at another one, 0.1 times 0.1. And we're asking, is that the same thing as 0.01? And Python says that it's false. Well, why is that? If we do 0.01 or 0.1 times 0.1, we see that it's close to 0.01, but there's a 2 added in here at the end that is not what we expected. So that's an error in the computation. Another situation we might encounter would be on trigonometric functions. So if I import numpy smp and I say np.sine, like the sine function, of np.pi. So the sine of pi should be 0, right? But Python thinks it's 1.2 times 10 to the minus 16. So there's another type of error that we're encountering. And finally, let's look at another one. If we do np.square root 1 e minus 16 plus 1 minus 1, it says it's 0 when it should not have been 0 because we had this additional term right here. So to understand why these errors are happening, we're going to need to understand more about how these numbers are getting stored within the computer. So we can start by taking an example number like 2162 and breaking that down into its pieces. So for example, we'd have 2 in the 1000th place, 1 in the 100th place, 6 in the tens place, or 2 in the 1 place. And we can rewrite that as 2 times 10 to the 3 plus 1 times 10 to the 2 plus 6 times 10 to the 1 plus 2 times 10 to the 0. Okay, nothing fancy here. And we could also put this in more of a table format, as you see at the bottom, where because these are base 10 numbers, the numbers that you're used to thinking about, each of these bins can have any value anywhere between 0 and 9. So in our case, it's simply 2, 6, 1, 2, and for the 10,000th place, it'd be 0. Okay, so this is a table-based format for storing a number in this system. So that's not too challenging because you're used to thinking in base 10. But let's think about now in base 2, where an individual value, these little bins, can have a 0, which corresponds to false, or 1 that corresponds to true. And while each of these can be only 1 or 0, they correspond to different values in base 10. So 2 to the 0 in base 10 would be 1, 2, 4, 8, 16, 32, and 64. So that a 1 in this place counts as 64 in base 10. And so using this little table, we can fill this out, and we see that there's a 1 in the 64 spot, an 8 in the 8th spot, a 4, or kind of 1 value in the 4th spot, and a 1 in the 1st spot. And so if you add these all together, we can convert this into the base 10 equivalent. So do 1 plus 4 plus 8 plus 64, and you should get 77. So this shows you how you can break this down and convert into base 10 units. But integers can't just be positive, they can also be have negative values. And so in the next numbering system, we're going to say that we're going to use 7 bins to store the magnitude of the number. And by bins, another word for that is 7 bits. So 7 bits of information in the computer. And we're also going to use one of the bits to store the sign of the number. And so that's going to be using the equation -1 to the x. I'll explain that in a minute. And that together, the information for the sign and the magnitude is going to combine to be an 8-bit or 8 pieces of information being saved in order to store a 8-bit signed integer. Okay, so let's take a look at a few example numbers here. So if this one is 0 in the sign place, then -1 to the 0, right, is just 1. So that means it's a positive number. If we use the arithmetic that we used previously, would say that 1 times 2 to the 0 equals 1. So there's 1 in base 10. Similarly, if this again has 0 in this spot, so there's a positive number again, and it's 1 in this spot, so it's 1 times 2 to the 1 equals 2. But now in this one, we have a 1 in this sign spot. So that is going to be -1 to the 1 equals -1. So that means that there's like a negative number. So we've got a -1 times 1 times 2 to the 0 plus 1 times 2 to the 1 equals -3. That's how we got a negative number from this. And finally, if all of these numbers were filled up, and there's a 0 here, so it's a positive number, then we would say that that equals 127. Or note here that this had 7 bits for the mantissa, so that its number was 2 to the 7th minus 1 in terms of its base 10 maximal value. So what range of values can be saved in this system? Well, 127 was the largest, and then the most negative would be a -127. If all of these were 1s, we could get 127 as shown here, or if this value was 1, that'd be a -127. So we can get values -127 through 127. We can't store numbers that are bigger than this range because we're only saving 8 bits. So that's a quick introduction to how we can look at integer values. In the next video, we'll look at how to store floating point values.